over the disk, switch over the disk, kill the, I need to stop the, I wonder why I'm not seeing the camera. Camera. Just a second, Ray. For some reason I lost our video.
Yeah, problem.
It is a problem because it was working perfectly. Screen share. This is what I'll do is you may have to re-enter it. See this? We lost our camera. Sorry, one more time.
Jack.
Yeah.
We got that. We got sounds. All right. All right. So welcome everybody to our third TWed of the spring 2016 term. Today it's Rui Yan that's going to give us a actually it's an update on your streaming reasoning work. And we're really looking forward to it. It's each time Ray presents this, there's a lot more depth, a lot more thought, and so we're looking forward to a couple logistical things. Please feel free to grab pizza from the back. This is being streamed live and being recorded for posterity, so just keep that in mind when it comes to question times. Please feel free to ask questions. Rock and roll.
Thank you, John. So hello everyone. I'm really happy to present my ongoing work.
So you're not sharing right now, by the way.
Okay.
I'm sure you may have to re-enter the.
Yes, me?
Yes, you're good. Thank you.
So it's a pleasure to present my ongoing work. So that means discussions and criticisms are usually encouraged. So the contents the title is Semantic Importance in Cached String Reasoning System. So that exactly 3 parts. I'm going to cover the string reasoning systems and a cache-enabled string reasoning system and semantic importance. So the contents, just overview of my talk. I'm going to cover the motivation of the string reasoning, and then the object of the string reasoning. That is the RDF streams, which RDF encodes streaming data, and also I'm going to talk about existing systems in this field, and then I'm going to dive into why we use cache in string reasoning, which is sort of a new way to do the string reasoning stuff. And I'm going to compare a window and a cache. A window is typically a traditional way of doing string reasoning. And also I'm going to cover my proposed cache-enabled string reasoning framework. So the last but not least, the other important section of my talk is the semantic importance and data eviction. I'm going to cover why we care these two and their definitions, and why ordering can play an important role in that part. So the string reasoning. So during the past decades, the semantic web is usually concentrated on the static data. So we have the RDF model and and some an ontology language and some other languages that is powerful enough to model the static data on the web. There's tons of proposals and methods have been proposed during the past decades, including linked data, which try to structure the data on the web and link them using unique URLs and link different repositories. You can imagine the big linked data cloud picture. So we actually have some issues when we are applying semantic web technologies on static data. That is scalability issues. With huge amount of data, how do you scale your method so that method will not fail, right? And performance issues. Again, with the size of data, your system should be performed really quick and efficiently. And third one is data management issues, also relates to the volumes and the size and other aspects of the big data. But currently there is a trend identified by this guy, that we are actually shifting from big and static data into small but highly updating rich data. So, for example, you have the Facebook and Twitter tweets usually as an example from the social media domain. But this kind of streaming data are everywhere. So for example, when you are switching the TV channels, you are sending a streaming data, right? And when you click on a mouse, you are sending the click streams. These are all examples of the streaming data. These are the data and the metadata are small size, but they are containing rich enough information. Just consider a piece of tweet that contains URL, contents, hashtags, pictures, metadata, stuff like that. So there's a lot of rich information going on, and they are highly updating. So that means when the fact that you keep tweeting, keep Facebooking, and everything else is actually reflecting your most recent status by the streaming data itself. So, stream processing is a domain that is not new and has been developed for a long time. So proposals and works from this domain is basically able to process streaming data with large volume and high update rate. And their primitive operators such as joining, aggregating, and filtering is doing really well to process the streaming data. However, they do not provide any reasoning ability. That means you cannot gain the insights from the streaming data. What you do with those work in stream processing engines do is basically manipulating the data, try to combine them or filter them and give you some result from that. And semantic reasoning performs basically on the static data. We usually have a bunch of rules and reasoners and the data, background ontology, logic, whatever, and mix them together, and you can gain insights from those data. But they are not typically applied in a streaming domain or scenario. So the motivation of stream reasoning is basically try to incorporate the advantages of both stream reasoning and semantic reasoning, and is identified in 2009 by Emmanuel Delvaux. So it aims to bridge these two domains so that it can provide full reasoning ability for stream processing systems. RDF streams, which are the object of the stream reasoning systems. We have static data, and static data can be modeled by RDF, which has logic and can be machine read understandable. But how about the stream reasoning? How about streaming data? The streaming data, actually, during the past decades, the best practice of modeling data has been only concentrated more on the static data. But streaming data features large volume, rich contents, different updating rate and heterogeneous. In order to precise those, RDF, the success of RDF in the static data inspired people to extend RDF to model streaming data. And that comes the semantic streaming data, also called RDF streams. RDF streams are typically a data item that is either a triple or the graph of multiple triples. And the graph can be identified by unique URL, which is graph ID. And since it's streaming data, that means it should have some time element. And we have to be really careful about the association of time with the data atom, so as to preserve its decidability, because time is really kind of really flexible thing. So for example, like in a static database, Alice, a person, cannot be tall or short at the same time. That's a contradiction. However, as you can consider this thing. If you consider this thing in the timeline, Alice can grow up. Alice can be tall at 18 years old, but can be short at 9 years old, right? So time is really kind of interesting to play with. And the application time, we can leverage a timestamp which is a temporal identifier that can be associated with the data item. And the application time is a set of timestamps. So that means a data item can have one timestamp or multiple timestamps. Like an obvious example will be given later. Next slide. Okay, so this is one example of this semantic data streams. You basically have the stream, and you have those data as triples. And for this particular example, each data item is not associated with a timestamp. So that it is only an ordered sequence of data items. And the order can be exploited to perform queries like, does Alice met Bob before Carl? So this before is actually try to query something at a time. But it never gives you exactly like 5 minutes before, 10 minutes before. It only can tell you yes or no before, yes or no.
But for that to be true, though, even though there's no time stamping, there's order.
Yeah, the order sequence implies just the order.
But normally with RDF, it doesn't matter.
Yeah, that's true.
So you're saying that there is some implicit. So even here you're imposing some order, even if it's not time.
But no, considering this is a RDF streams, Alice cannot. It is possible that Alice can meet all of the person at the same time, and also Alice can meet all of the persons separately, and that has an order. Meet you first, and meet him later. Then that forms a stream. That stream is not necessarily stamped with a timestamp, but it is coming with an order. So we can answer the question whether Alice met Bob before Carl or later. Something.
Okay. So what you're doing is you're defining something called an RDF stream.
Yeah.
And that has order. So
yeah, that's
a property of an RDF stream is that there's order.
Yeah. And this is actually one timestamp RDF data stream. Each item is timestamped with one timestamp. So for this case, it is this timestamp indicates that Diana is with Carl at time 9. And last but not least, we actually can assign 2 timestamps to a single data atom. So that means, for example, we have Alice is with Bob at time 1 and 2 time 5. Alice say goodbye to Bob. We can modify this kind of event with an interval of time, with like a beginning timestamp and ending timestamp. It can allows us to answer the queries which are the meetings that last less than 5 minutes, something like that, which gives a more concrete sense of what's going on there. And existing systems. Stream reasoning processing has been the domain of this has been developed since 2009, and there are some proposals that some of them like C-Sparkle, C-Pulse, and Flow, and String Sparkle, EP Sparkle, this, and this are extension of the standard Sparkles. So that means they took the standard Sparkle algebra and add their own flavor of Sparkle arguments to make things happen. So for example, C-Sparkle, they actually use some from stream. They incorporate a new argument called from stream to incorporate the data streams from a unique URL that is identified by the streaming source, stuff like that. And EP sparkle identified as QL to associate different events, so that you can query against the event stream. The continuous extension of the sparkle. So sparkle query is actually one query, one answer, and the query is sent after data is available. But in a stream reasoning scenario, we have to continuously answer the sparkle, and the answer should be continuously and reactively provided by the system itself. So that's kind of this is stream reasoning is not a passive system; it is a reactive system. One query, multiple answers will be provided as the stream data comes into the engine, and the data the result of the query will be updated as the data enters into the engine. And the query is a registry in the query engine. The registration usually happens before the data arrives. The real-time response is usually required, because in a stream reasoning scenario, you have to be really fast to process the data so that you can give the data to the user. Give the result to the user really fast. I'm going to cover C-Sparkle as an example of existing systems. C-Sparkle is continuous Sparkle. It is an extension of existing standard Sparkle queries, and add RDF string as a Sparkle data type. An RDF string in C-Sparkle is defined as a subject, predicate, and object, and single timestamp. It inherits the execution model of continuous query language, which is work done by this group. And it leverages a window and a step. A window actually have different types, like a time-based window. So in this window, a window is like a length of time period. And the count-based window, so the window size is count, it's like a certain number. And there are also two types of window, like sliding window is when window step is smaller than the window size. And tumbling window is a window step equal to window size. The architecture of the C-Sparkle is basically you have the C-Sparkle query, and there is a built-in translator that can translate the static part of the query and the stream part of the query. The static part of the query is basically the standard Sparkle query, and it sends to the RDF store. And that RDF store contains some background ontology, and also the streaming part of query. And there is an open source stream processor called Export, and these two systems can process the two parts of the C-Sparkle query and combine them together to give you the continuous result. The execution model of the C-Sparkle features the S2 operator, R2S operator, and Sparkle operator. You have this RDF streams coming in, and you have this string to relation operators to get a portion of the RDF streams, and fit into this RDF mapping, and you execute Sparkle against this mapping, and when you have the result, you can choose to string the result back to the RDF streams using relation to string operator. So here comes the second part of why we are using cache. So as an example before, we know that C-Sparkle features a window, and window is actually one of the main dominant method to isolate a portion of this unbounded RDF streams to process them. Right? Cache is actually functions similar as window in terms of stream to relation operator. It tries to separate a portion of that of the unbounded streaming data and grab that into the processing engine. However, they are different in consumption rules and data eviction rules. This is a typical window, picture. But you have both sliding window and tumbling window. Depends on the relationship among the window step and window size. So, for example, in this sliding window, you have only data here as the width, which is also called window size. And you have the beta here as a window sliding step. So each time window will slide along the data, and these are data items, and this is the timer. The window will be sliding along the data with one single step. for the sliding window, since the window width and window slide, this guy's bigger, so there will be some overlapping RDF data items between two moves, right? You can see here, like window size is like this, but window slide is like this. So each time it moves, S3 and S4 will be overlapping, right? But Handler window is basically there's no overlapping elements between moves because the step and the size is the same. So it moves like this, and then later on moves like this. So there's no overlapping. Right. From this, you can see that a window is basically consumes the RDF streams by sliding along the data, and it evicts the data only depends on the order of the data. That means the I5, I4 first in, first out. Because this S1, S2 first are the first to come into the window. So that when the window moves, S1, S2 will be evicted first.
So those are S1, S2, those are
data atoms, the RDF streams. However, in our cache system, there's a different story there. So this is an early work of mine that tried to leverage cache to do a stream reasoning work. So there are 4 stages in this framework, and this is the streaming source that streams data into the overall system. That streaming source features like this single row is a triple or a graph of triples, and this tau A1, tau A2, this is the arrival timestamp, meaning that the data when the data arrives the whole system, and this is the expiration timestamp assigned by the streaming source, meaning that the data when this piece of data will be expired. And G1 is a unique graph identifier that hosts all triples in this single data item. Right? And if you have those streaming data like this and stream into the overall system, and the cache will consume all this data, depending on the size of this cache, the data will be sent by this data consumption component into the cache, so that cache have all this data, like with n graphs, number of graphs, which is this cache size. And then you have a query pre-registered in the system, so that once the cache is full, the query and reasoning part will begin to execute. So combined with the background ontology and together with the cached data, you can do querying and reasoning. And if your query requires reasoning, you will actually give continuously output the query result, and also combine it with the background ontology to give you the reasoning part. And the third stage is the reasoning explanation component, which explains the reasoning. Why we want to explain the reasoning? Because we want to see which part of data is participated in the reasoning, so that we can make some decisions to preserve that part of data, because that part of data contributes to the reasoning, which is which is a required kind of process to answer that query. Right? And after we have we obtain the information of that part of data who participate in the reasoning, then we are trying to re-rank them according to their reasoning participation and also their expiration timestamp. We re-rank them so that we know that if the data rank on the top, that data will be more semantically important. So that means we need to preserve that part of data. And the data ranked on the bottom should be something not important and less important. So we may consider to delete those data from the cache to make some room for the new incoming data. Right? And this framework keeps going on in the loop. So that provides you the continuous way of executing the query, giving the result, and processing the streaming data. So in this framework, how many assumptions do we have? We have the assumptions that the streaming data has 2 timestamps. the arrival timestamp and expiration timestamps. And we assume that this piece of data is packed in the unique graph ID. Both unique graph ID and expiration timestamps are assigned at the streaming source. And this arrival timestamp is assigned when the data arrives into the system. Well, I mean, actually, this framework can be general. Like if expiration timestamp is not assigned by the streaming source, or the graph ID is not assigned by the streaming source, the system will always assign the data with an arrival time order, because the data will arrive in the system. And like each single triple will be assigned with an arrival order. And in this time, the system will not consider expiration time, to only consider the reasoning participation and arrival order. Like this data will never expire. If the data participates like 10,000 times in the reasoning explanation, that data will be likely preserved in the system and will never expire and will never be evicted. And data eviction. Data eviction is a process
before you go on, just go back 1 second. So just first of all, those URIs, those are just designators for the
graph IDs just
right. So are those graph IDs or are those
graph IDs?
Those are graph.
Graph ID 1.
Oh, I see. Graph ID.
Yeah. Graph IDs. Data eviction. So we define data eviction as a process to drop some cached data to make room for upcoming data. Because we have a fixed size to cache. That means the cache will be full, and when the cache is full, everything will be executed, data will be processed. But after process, we need to evict some data to make room for newcomer data to drive the continuous execution of the query. But we have some open questions here. First of all, choosing which data to evict. Like, according to what you choose that data to evict, and that's kind of open question. That's also a research question. The second one is how to evict the chosen data. Because the algorithms to efficiently evict the data will affect the accuracy and efficiency of the system, which is also an open question. How many ways, and if possible, can you compare those different ways, such that people can know which performs better or not? And we propose semantic importance. Semantic importance is defined temporarily in the last paper as the indicator to measure the contribution of the data to the query results. As an example, I covered in this graph why we use this reasoning explanation component, because we want to see the participation status of the data involved in the reasoning to evaluate its contribution to the query result. However, that is only one example of what a semantic importance is, because semantic importance is defined in this. This is really an abstract definition, but it has a wide scope. So that means those wide scope can basically classify into domain literate and domain agnostic. In the domain literate scope, you can see a data is important if it participates in a query, including the frequency of the participation and the recency of participation. And similarly, you can see the reasoning participation of the data. Whether this data is more actively participating in the data, participating in the reasoning, then we are more likely to preserve it, right? And we can also, use some probabilities to predict if that piece of data will contribute more in the future, like near future, based on its previous performance, right? And we can also, use some precisions, reliabilities, and popularities to determine if data is more important. Like, for example, if in the popularity, and if we apply popularity in the social media domain, popularity can be calculated by the ratio between tweets and retweets, that kind of thing. If if the retry is bigger, then that means it's more popular, then we are more likely to preserve them, to serve our purpose. And definitely we can leverage the provenance, trust, and certainty to preserve the data, and we can also use some attribute values like a type, geolocation, latitude and longitude, and some other stuff to determine what part of the data could be considered as important and why we want them to be important. Domain agnostic methods could be like temporal order, like arrival order, expiration order, and cardinal order, like data appearance counter. Like if the same data keeps occurring all the times, that probably we need to preserve them because they're everywhere. So that's really a lot of possibilities to determine what the semantic importance is.
So let's sort of pick this apart, because this is like the dilative crystal of the whole thing right here, right? I mean, this is it. Right? You've squeezed it all down. All we have to do is figure out semantic importance.
Yeah.
Now what is it, right?
Yeah.
And so intuitively, in the domain literate section, the first couple, they make sense because it's consistent with classic cache definitions. Whether it's it's the memory cells that were touched, it's the block of bank of memory that was touched. It's sort of that there's an analogy between classic cache design and algorithms and what you're suggesting with those. So it's kind of, okay, that makes sense. Okay. But then what you're doing is you're kind of branching out and you're saying if there's certain semantic relationships that, or no, let's turn this around. You can define certain semantic relationships which dictate whether or not it should be kept around or not. That's what you're saying. Is that I mean, some of them are going through mind. Were in my mind are things like that attribute value. Is this?
Yes.
Is there something? If there's some relationship with the data that suggests, so you're sort of like, ooh, we're getting stuff here, so we have to keep it around. And stuff we don't know.
Yeah. Here was it. So so the first like three parts are like compared to the others are more domain agnostic because they are not restricting a certain use case. Query can be Spark query, and every use case uses Spark query. So that is more domain agnostic compared to the others. But when you apply things in different domains, you have to consider a more domain literate semantic importance in order to serve a purpose. And that's why I kind of want to propose this stuff and would like to mention their potential use cases so that people can understand that in different domains there's a lot of interesting potential semantic importance there that we can use.
So when this came around before, when you were first kind of talking about these ideas, I raised this question of how does this relate to cache, classic cache design? And I think the next step, as I look at this, is you really need to define those use cases. Find real examples. How do they play out here? And then see if there's some way that you can sort of simplify it. Is there some generalization of that? Are these really different, or are they really kind of the same somewhere?
So I plan to do a use case thing, like in the social media use case, what are the semantic importance? I'll cover like what determines the semantic importance later in this talk.
Okay.
So that we can discuss.
Sure.
Right. So later on,
we follow up if you don't get an answer.
I thought people were going to say amen.
We have so many choices for semantic importance, and a single value for semantic importance is fine, right? But there are cases where semantic importance is complicated. Right? So, as an example that I covered just now, we have the streaming data as PO, the RDF data, the triples, and arrival timestamp and expiration timestamp. Right? We want to see whether this piece of data is actively participating in the reasoning process, but we have to both consider expression time and reasoning participation. Especially we have to pay close attention to the expression time, because that defines the valid period of the data. And if data is invalid or expired, all the results it contributes to are invalid, right? No matter how hugely involved this data is in the reasoning process. So that means we need to have some sort of a priority among those semantic importances, right?
So there's actually another question. What about a page fault? I mean, if it's not there in classic design, something's not in the cache, you don't say, oh, you say, you pull it out of, you retrieve it.
Yeah, well, we don't usually consider things that is not in the cache, because cache, as a operator to isolate a portion of the streaming data, the cache data are used to answer the query, and that's it. I mean, if the queries could not be answered by the cache data, then those cache data are less important and probably will be evicted soon, so that upcoming potential useful data will get in the cache and get the query answered. There's no page fault thing, because
right. So what you're saying is, if it's not there,
the data will be not answered. The query will not be answered.
The query won't be answered.
Yeah,
but
there's
do you
no
do
result.
anything to adapt your cache rules such that the next time similar data comes around, maybe you change those rules so that it's there?
That actually depends on the kind of eviction methods and eviction rules, and also the data structure in the cache, stuff like that. That would be more low-level stuff.
Well, I guess it's a question of importance. Okay, so what you're saying is, if it's, so you have some definition, stuff gets evicted, query comes around, the stuff is not there. Okay.
Yep.
But that query is telling you that maybe the stuff is important. So therefore, you need to modify. It's become semantically important. So maybe the stuff that was in the past, okay, that's past, okay? But now, and it's gone because it wasn't important. But now it's, next time around, similar data is important because you put in a query. You've added to the query set, and this is now important.
Well, I guess you are considering different queries that can be executed in the system, but we are only considering one pre-registered query that is being executed in the system. Well, I mean, in your case, you can have multiple queries, maybe this data is not important to one query, but maybe important to another query, right. But this data is gone, but this is not the scope of this work. It could be potential future work, but as far as I can see, the stream reasoning world does not do multiple queries. This is what I see.
That's a great answer. Sorry, it's not in the scope of this work.
But that's true. I'm not trying to.
No, I hear what you're saying, but I guess I'm possibly thinking of a different.
That's good. Case, that's right? Good. I mean, that's good. That's useful. Right.
So all right.
Yeah.
Cool.
And that's why we propose the semantic importance priority vector. What is a priority vector? It's a ranking of the alternatives that indicates an order of preference among them. So, and the semantic importance priority vector is composed by several, semantic importance value, SI1, SI2, SI3, SI4, but we are giving the priority to the front ones, right? For example, we have discussed expression time step and reasoning participation. We are more concentrating on expression time step. Although this reasoning participation is also important to contribute to the final determination of whether to evict the data or not. But we are more concentrated on this because, once this data got invalid, the result will be invalid and will harm the whole overall system. The order matters. Why the order matters? Because order helps to scope things down, right? It can also, so once the things are scoped down, the inferencing will be scaling up, and the runtime and performance will also be raised. One example, like we have this query. Okay. What's the most popular local restaurant among your Facebook friends, right? There are some restrictions on this query. Like your Facebook friends, local, and most popular. These are like indicators that we can order the data, incoming data, in a way that those data can be sort of filtered out to be relevant to this query. And we can filter out all the problem data that is not relevant to this query, right? The social network streaming data keeps coming into your system, but only those ordered by geolocation, restaurant rating, and direct different relationship will contribute to the result, right? So that is one example of how order can scope down things and help processing and reasoning to be more efficient. So the cache data can be ordered according to their semantic importance, right? So we are leveraging this ordering and the semantic importance. Example, like the higher the data rank, the more semantically important they are. This is something we define in our system, or you can define whatever, right? You can define, the higher the data rank, the less semantic importance they are, whatever. You can define whatever. But the semantic importance helps to choose which data to be evicted, which means that those data are less semantically important, coupled with the ordering. So together with ordering, semantic importance can contribute to the which data should be chosen. The first question that we want to ask, right? And then I'm going to talk about the eviction rules. So we define the eviction rules as the eviction rules define the eviction behavior and makes the eviction decision. So what's the eviction behavior right there? Eviction behavior is like how the data is evicted according to which data structure, stuff like that. So eviction rules are related to the data structures used in the cache to rank the data. We use data structures to rank the data according to their SIs, right? So for example, we can use pre-RTQ, right? We can use that and rank all the data by considering the expiration timestamp and resident participation frequency. And the more the participation frequency is, and as long as the data is in a valid period, we can rank them, and we can evict those, not like frequency is 0 or 1, compared to other bigger frequencies. And if the data is expired, no matter how big the frequency is, it will be evicted as soon as possible, right? And we can also use some like threshold-based stuff. So when the data participates in the reasoning, we can have some like increasing counter or decreasing counter method, and we can have a threshold to be like 0, and if the counter is -1 or -2, like below 0, then there is a decision can be made to delete those data.
I think you need to be in a future version of this. You need to be very explicit. I think, while in general, I think it would be helpful. That in the next churn of this, we should work an example all the way through. Okay?
Yeah.
You should, so you're always talking relative to the example.
Mm-hmm.
Possibly even an example which you use to explain some of the background work, and then develop these ideas. But this, and I think that maybe the previous slide as well. But as you get into this stuff, you need to really be very clear. I'm clear by so on the eviction thing, show exactly, illustrate that very precisely.
Yeah.
Because it's easy to wave your hands and
right.
fool yourself into thinking it's working.
Yeah, when I'm staring at this slide, I feel like maybe I can show some pictures in the examples so that people cannot be lost or confused by the.
Well, do you have?
stuff.
Well, yeah. I mean, do you have any right now, or?
No.
Okay. Well, you should. I mean, you need to. I mean,
Yeah.
This is the kind of stuff that, because otherwise it's just you saying it.
Yeah, that's true. All right. So the last slide is about what determines the semantic importance. I'm trying to answer your question, John.
Yeah.
So, since semantic importance has a wide scope, how to choose the semantic importance in your system? So I think semantic importance is defined by both your data and your query, actually, right? The data is basically, you have to pay attention to the data timestamps and the domain agnostic aspects, including expiration and arrow timestamp. And, and also the query. The query, actually, in order to answer that query, you have to find some data that is relevant to that query and mark them as important, right? So, like, as the same example, what's the most popular local restaurant among your Facebook tweets? The semantic importance should include the geolocation, friendship, and restaurant rating to consider those related information as a semantic importance and apply into our system. That's my thought. That's my thought. And it could be other things that can be to determine the semantic importance, including like eviction rules. Because when you try to design the system, the eviction rules, the data structure in the cache are all fixed, and maybe you have to do some optimizations to allow the data structure and semantic importance to work more smoothly, whatever. So that could be one thing, but that thing is not that big according to compared with the data and the query. So
Is there a way to think of? Of course, it is because you described it this way. But thinking of the. So first of all, another thing you need to have is making clear the assumptions. One of the assumptions. This is why we were having that sort of misunderstanding earlier. Is you're assuming that the query is static, right? It's not a. This is not necessarily a dynamic system where queries are coming in. That was my misunderstanding. I'm assuming people throwing queries and it changes it. I think you're thinking it's more of a static thing, right?
Yeah.
So given that assumption that the query is static, you've got the stream of RDF coming in. You're using you can think of the RDF is coming in, and this is this humongous graph, which is kind of intractable. So you need the cache to make it scale. So you're building this graph, and that graph is first and foremost is relative to your query. So that's kind of what you mean by semantic importance. Is you've got this this query. Essentially, it's always a query. Semantic importance is a set of queries or a set of rules, and this is building this graph, this small graph, which is what's important, but it's more than that. There's probably extensions, so it's more than what's specifically being asked for by that query. It is what's being asked for by the query, but it's more than that. And so it's a subgraph that kind of has this relationship to the larger graph through this through these queries, right? That's essentially what you're. So you ought to be able to depict that. You ought to be able to depict what you mean by a cache. You might want to call it the cache graph or something. I don't know. That's up to you. That's up to you and your boss. Okay, but I'm just saying. Thinking of this as you've depicted it sort of conventionally as this set of this set of datums and that sort of thing. But from our semantic web perspective, it's a graph. Right?
Yeah,
it's a graph.
It's
RDF. It's a graph.
It's a graph. Yes, it's a graph of graphs. Yes.
Okay. Yeah, but there's some kind of relationships going on. Yeah. So I'll take it. I realize this. You're like, what is he? I'm not going to say yes because he's throwing this at talk. But maybe I should say think about that. Think about the relationship between this larger graph, this semantic importance in terms of queries and rules, inference rules, and all that kind of stuff. What that means, it always means a graph. Maybe it's a set of graphs, as you're saying. Which means you're thinking it's not necessarily tied together; it could be fragmented. Okay, maybe that's the case, but it's all graph stuff.
Right.
Okay. So I'm just thinking about that.
Yeah, sure. Thank you.
I mean, but the point being, and so if you use your rule, if you use this as your example, geolocation. Okay, there's certain geolocation characteristics which you're defining, and that's indicating semantic importance. So therefore, as this stream of data comes through, there's certain things that are going in the cache based on that. Okay?
Right.
So that's getting stitched together. So you've got this graph here, which is related by that definition. So these things are somehow, these are related. They're tied together. It's a graph.
Yeah, I mean that's a graph, but you always want to pick out those unrelated or less important data to evict them, because you have to
Well,
make
no,
room.
okay, so there is stuff that gets pruned.
Yeah.
Okay, so what you're saying is stuff gets in the cache and it gets thrown out. Okay, and that's the stuff that's perhaps on the fringes or somehow, or is disjoint from the other parts. So maybe the stuff that's more likely to stay is all nicely tied together. And the stuff that's comes in that's not related to this is sitting there on the fringe and is. So if you visualized it, you'd say, this is the stuff that's likely to stay. It's important. It's tied together. It's related. Okay, and this is the stuff that's going to get tossed.
Yeah, that makes sense.
All right.
All right, that's the end of my
Does
talk.
anybody else want to use up the oxygen in the room? Questions? Questions for Ray? Well, let's thank Ray. Thank you very much.
Thank you, everybody. Yeah.
It's definitely so we've got a very full schedule for TWeds this fall, but there still are a couple spots. If you're interested in giving talks, we have an open spot next week even, and I can fit you in if you're interested. But other than that, thank you. And
Thank you, Joe.
good night.
Yep.